to record the meeting.
Recording is
Awesome. Okay, today we are going to discuss these two problems, at least maybe the first problem here on the linked list. So last week we discussed about the linked list insertion, like determine if the intersect, basically, or intersection. So determine if the two linked lists are intersect or not. If intersect, where they exactly intersecting. That's the problem we discussed. And also we discussed about palindrome, if a linked list is palindrome or not. So these two problems already, we recorded, we discussed, and the recording is already available in the YouTube channel. I will send the link. I'll put it in the description. So today maybe we'll discuss this one: linked list special delete and insert. Okay. So first one is special delete, means it's not deletion. We already discussed about deleting a node. So this is about deleting a node without accessing the head pointer of the linked list. So you don't have access to the head pointer, but you want to delete a particular node in the linked list. So anybody heard about this problem before?
Last two sections, I think Soumya has posted this question, right? Maybe.
Yeah, yeah. Soumya, or I think Karanya, someone asked about this. Delete a node from a linked list without head pointer. So head is, if you look at here, head pointed, this head pointer pointed to the first node in the linked list, but we don't have this. We don't have head. Let's say we have a pointer that is pointed to either C or D, let's say, and you want to delete that C. Let's say you want to delete C. How can we do that? So anybody, like, here is a Geeks for Geeks algorithm is there. Anybody tried before? Anybody saw?
I tried only just deleting a node, but not this one, Suresh.
Exactly. Yeah, that's good.
Yes,
So let's dive into them. Same. Okay. So it's just a tricky problem. It's not complex problem. It is a tricky problem, and I think it's one of the famous interview questions in the past. I don't know whether they are asking now or not, but this is one of the interview questions. So let's that's the first one, and second one is insert a node at the correct position in a linked list of integer elements where nodes are linked in ascending order. Basically, you have a sorted linked list, simply saying there is a linked list is already sorted, like 1, 3, 5, 10, 12, like it's already in increasing ascending order. Now I will give you 4. You need to insert at the correct location. It should be in the same sorting order, right? So which is basically essentially insertion sort in linked list. So how to do this? This is also, it's not a big complex problem, but it's interesting problem. So let's discuss these two today. So first one is deleting a node. So before going to the main algorithm, I want to iterate about the previous one, like the deleting a node by using a head pointer. So this is the algorithm, right? I think we discussed 2 weeks ago. So I don't know, Vanilla, you joined or not, but basically this is simply saying, hey, there is a node. This is a method like delete the node with the data. Data is something like, hey, I want to delete number. Let's say here is the thing. I want to delete node 3. Okay, and we already have a head. Actually, there is a head on the top, head pointer here. Yeah, see this? This is the static head. Always, the head always points to the first element. So we can simply figure out. So let's say head points to the first element, and this here is the adding of the node, and here is the deleting of the node. So you want to delete with value 3. So what you do is basically, let me put this one aside. Yeah. Okay. So now what we need to do is we need to start from the beginning, and we need to see whether the data of the head is the what you want to delete. If I say 1, delete 1, just remove the head, right? We are going to remove the head and simply head equal to head dot next return. Nothing. It's very simple, right? But if you want to delete something, not head, if you want to delete 3 or 4, what we need to do is we need to do this while loop, where we need to start with the pointer started with head, and we need to check whether the next element is null, and is the value of the next is the data you want to delete. So let's say you want to delete 3. What we essentially need to do, which node we want to change? We want to change the
Second node,
node
right?
before. Exactly. We need to change the address of the node before the element which you want to delete. We want to, so nothing we need to do with 3, because deleting is simply, changing the links. We no need to worry about the deleting of the memory, because that will be taken care by the garbage collector, right? What we all need to do is we need to find what is the element before 3. What is the element before 3? And change the next pointer. So we need to change this pointer, point to the next element of the 3. That's it. That's what we are essentially doing here. The pointer dot next dot data equal to data you want to delete. Is the pointer already pointed to, let's say pointer pointed to 1, first node? Is the next node is the one you want to delete? No. Next node is basically 2. This is not what we want to delete, right? In that situation, what we simply do is we will simply proceed with the next pointer equal to pointer dot next. Now pointer pointed to the number 2. Now we will see, is the next node null? Yes. Is the next node data is equal to data you want to delete? Yes, because next node data is 3, right? 2 dot next dot data. Pointer is currently at 2. So next node data is 3, and this is the 3 you want to delete. At that position, what are we doing? Pointer dot next equal to pointer dot next dot next. Basically, pointer dot next equal to pointer dot next dot next. Whatever the address here, we are putting that address into this. That means we are pointing this to the next element simply. Whatever the address we are having for number 3, that address we are putting in the address of the 2 simply, right? So everybody understood this particular line. This is the main line which will delete number 3. This is the heart of the problem here. Vinila and Soumya, you
Yes.
got it, right?
Yes.
Yeah.
So,
Yes.
and yeah, once that is done, we will simply return, because we are done. So you already deleted number 3. Basically, the actual deletion will take care by the garbage collector. As I said, you no need to worry about this particular memory location in C, Java, and most of these languages. Of course, in C++, you need to be very careful about deleting this particular element. You need to write your own code. Otherwise, it will take care by the garbage collector. So that's why we are simply changing the links. Now, what happens if I say delete 10? 10 is not in the list at all. So what happens at that position is, sometimes after, like, you keep checking, sometimes after checking 5 nodes, the pointer will become next 5. Let's say pointer pointed to 5. So pointer dot next equal to null, right? So that will exit the loop. If the loop exit, that means there is no need found, like no node found with the value 10. If I say 10, it simply navigates all the way to the list, but it did not find the value. So you cannot even delete anything. This is the algorithm we discussed before. In this situation, you have the pointer to the head. You have full control. You can start from the beginning, and you can find the element which is before the element which you want to delete. But let's say this is the algorithm. The actual algorithm we are trying to solve is this. We have 1, 2, 3, 4, and 5. This is, so here is 1, 2, 3, 4, 5. Now what are we going to do is we have a pointer. Let's say, what is the pointer here? I think it is node to delete. So we are getting the node to delete completely. Okay. So we want to delete 3, and node to delete n to d, and to d is pointed to 3. So how to delete this? Because you don't have anything, you don't have head, you cannot navigate, you don't know how many nodes before 3, and you know how many nodes before after 3, because you can navigate from 3, and all the rest of the nodes from 3 are accessible. Only thing is, you cannot go back because it's a single linked list. It's not double linked list. You don't know the previous element. But the problem here is, in the previous example we saw, we need to change this address. How can it's possible? It's not possible, right? Technically, it's not possible. If you want to delete 3, you need to change the address of this guy, but you cannot access this node at all. So what is the best way to delete here?
So
Any
like
clues before I? Yeah, go ahead. Go ahead.
so like
Yeah, let's start the discussion.
position will be given, like which node we have to delete.
Yeah, node to delete. It's like node to delete is actually this whole node. They will give you the whole node. They don't give you like, hey, delete 3. It's not. So in this problem, they don't give you the data. They will give you the complete node. So node to delete is pointed to this complete this node. Okay,
Okay, so
you can you
so they
can you can
are
you can have access to the data. You can access to the next as well. Yeah, go ahead.
so like they are providing the reference that we have to delete.
Exactly. Exactly. Sorry, that's the correct word. They are providing a reference to the node which you want to delete, which they want to delete. So now how to delete the whole 3?
So like if position will be given, so like we can maintain one variable, and like we can iterate to like just before that position, like if position is given.
Yeah, but how can you iterate? But you don't have a head pointer. You don't know where the head is. You don't. There is no variable, or there is no pointer available which points to the head node.
Okay.
You cannot start the iteration. That's the main problem here. Right? Without head, that's the main algorithm itself. Like without
Yeah.
accessing the head pointer of the linker list. It's a kind of tricky question. It's not like it's not traditional thing what we do in the real processing basically.
Yeah.
So okay, any other thoughts?
Can we create a dummy header in between of the mid of the data? I don't know
Dummy
also.
header. So yeah, the
Temporary.
problem here is the dummy header for what?
The temporary pointer. Uh,
Mm-hmm.
can we
Points
have
to points to which node?
the first node?
But first node we don't know the address, right? You don't know the address of this node. That's the main intention of this one. So you don't know where this node is, and you don't know where the rest of the nodes. You have only one pointer, one reference, which is having the node to delete. Okay, I will start revealing the answer because it's like funny. It's not like too much thing in the algorithm itself is funny algorithm.
So
So the main
like
thing
one
here is,
yeah.
yeah, go ahead.
So like we know which node will be null. Like
We know
like
which exactly. We know which node will be null. Yeah, this node should be null. Yeah, like null in
like
the sense we need to remove that node actually. Yeah.
yeah. But like but we can't iterate, so we don't know the head. Continue, please continue.
Yeah, what to do in that situation? So simple here. I'm revealing the answer. Okay. So basically, as I said, we need to remove 3. Right. We need to remove 3. We have to update the address of 2. We don't know where this 2 is. We cannot iterate from the head. So what we can do is, as I said before, you can access rest of the nodes from starting here. Right. Since we have reference to node to delete, by simply navigating to the next element, you can go to the next element, you can go to the next element. There is a possibility to go forward, right? So what we can do is simply is we can copy the data from here to here. We are making like, hey, it's not 3, make it like 4, and you can simply delete this node. That means you can change this address to this address. Is that equal to deletion of 3? It is, right? Now the final value is 1, 2, 2 points to 4, 4 points to 5. 3 deleted. Magically 3 deleted, right?
So uh, like we have changed the reference that is stored in 3.
We are not changing the reference, we are changing the data here. So that's the main difference here. So basically, as I said before, right, so we have nodes like this. We have 3 here and we have 4. Okay, so 3 points to 4, 4 points to 5, right? So now what I'm saying is you want to delete this node, right? So now what we can do is, since we don't have access to the previous node, what we can do is we can override this data. Anyway, this node needs to delete, right? What we are doing is, okay, give me the data of the next node. What is the data here? This is 4. Put the 4 here. Okay, we are changing the data of this node. Now the value here is 4, and now address. Now what is the list here? 1 2 4 4 5. 3 already gone, right? 1 2 4 4 5. Now we don't need the 4, because whatever the data here we already copied here. Simply, what is the address here? That address we will put it here. That, let's say, the address of the 4 is like 1145 or 1111. This address 1111 in memory goes to 5, right? That memory, that address we are putting here. That means the next node will go to 5. So ultimately 1 2 4 5 is the list. So simply 3 removed, right?
Yeah, got it.
Is it clear, Soumya and Vanilla?
Yes.
Yes, please.
Yeah, it's a dirty solution kind of thing. Like, you don't believe like it's possible, but it's like, what is the point of you're not deleting node, you're copying the value, but ultimately what happens is that the final result is, we need to see. If you see the final result, you technically you did not delete this node in the memory. You still, that node is there. Whatever the address, let address of this node is 145 something in the memory. That node is still there. Finally, that the only thing is the value changed in that node. Previously, that value, this is 145 in the, let's say that's 145 is the address of this node in the memory. Previously we have 3 here, now we have 4. That's it, right? So
Yeah,
this is the algorithm. Yeah. So the, now let's say the problem here, there is one more problem here. This is a kind of dirty solution, because you cannot delete all the nodes. Let's say you can delete, with using this algorithm you can delete 1, because you can copy the value from 2 to 1 and simply 1 gone. You can delete 2, you can delete 3 4, but you cannot delete 5. Can you delete 5? Because there is no next node of 5.
yeah,
You definitely need to change the address of the 4. There is no option. You got it? There is no option. Like, if 4 is always pointed to this address. So with this algorithm, there is a drawback. You cannot delete the last node, like last node of the linked list. Is that clear, or any clues or any other ideas you getting to delete number 5? Even if you create new node, you will put new node 5, but you cannot, there is no way. Like, the only thing is you have to update this particular thing always goes here. Only thing is you can make 5 to 0, but or you cannot make the node to null.
yeah, it's clear. So like we cannot reach the fourth node, like the node with 4 data.
Yeah,
Yeah,
exactly, that's the thing. So cool. So I think you, all three of you, think clear on the algorithm. Let me know. If not, I'm going to show you the solution here. As I said, simply, here is a node to delete, and if the node to delete is null, simply return. If the input itself is a null, this is a base condition, right? If the input itself is delete null, hey, how can we delete null? Simply return. Nothing here. Now the next question is, if node dot next equal to null. Node dot next is equal to null. That means, what is meant by that? If the node dot next equal to null means you are asking me to delete the last node, correct? If I take
yeah,
any of the nodes, The next value is not null. The next value for next reference, basically next is the reference, right? So reference to the next value is not null here, not null here, not null, but only thing is null here. So that means if the node to delete dot next equal to null, that means you're asking me to delete the last node. I can simply say this is the last node. We need reference to the head. We cannot delete last node. So that's the simply a write line, like a console write line and return. You cannot do anything. So next thing is the main thing. Okay, now you know you want to delete node to delete, and you are copying the data node to delete next dot data. Whatever the next elements data, you are putting in the node to delete data. And the next one, node to delete dot next equal to node to delete next dot next. Whatever the address of the next element, we are putting that as the address of the node to delete. It's very simple, just 2 lines. Is it clear?
Yes.
Yeah.
Yeah.
I think we
And
can
as I said,
same
yeah,
problem in
go
double
ahead.
linked list, I think so.
Yeah, in double linked list, it's very easy. No problem. You can simply go back. So in the double linked list, there will be 2 references, next and previous. You
Yes.
simply say, hey, what is the previous? And previous dot next equal to next, like current dot next. It will automatically, navigates to this one. So yeah, we will also do that. So next topic is like maybe next week. I'm going to start couple of problems in double linked list. So that definitely one of the things we can do. So yeah. And as I said, like you no need to delete the, basically you no need to take the next node, like 4. You already copied 4 value from here to here. So technically we need to delete, or we need to delete the next node, which is not needed, because Java and C sharp, everything will be taken care by garbage collector. So after 5-10 minutes, after like couple of minutes, this node, there is no reference to this node anymore, right? So if there is no reference to, no one in the algorithm, no one in the program is not using this node, it will be automatically taken care by the garbage collector to clear that memory. So it's simply 1 2 4 5 is there. Okay, so that's how, just 2 lines of code, very easy. And yeah, any questions, Monique or Soumya? Is it clear?
Yes, Suresh.
This
Yes.
need to be looped, right? Where we are doing the loop, suppose if we want to delete the 2, we need to, suppose if we want to delete the 2
If
again,
you want
so
to delete
he has to
2,
copy the 2,
yeah, yeah.
and 4 has,
So
and
if you want to,
yeah, like 4
if
has to
if
copy
you
in
want
3 and 5 has to copy in 4, then we need to loop, we need to do all the stuff, right?
I thought the same thing, but it's not required. Here what I'm doing is I am copying the value of 3 to 2, right? This becomes 3. Now I no need to copy the value 4 to 3 and 5 to 4, because I can simply navigate like this. Like, that's what I'm doing. That's what I'm doing on line number 127. That's a good question you asked, actually, because I thought initially, I thought the same thing. We need to do the loop and we need to copy all the elements. Just like arrays, if you are deleting the arrays, you need to do that, because array element is a pre-assigned, and it will not be taken care by the garbage collector until you completely clear the array or stop using that particular array element. But in the linked list, right? What is the next value of 3? Right? You can simply say, you can change the link to here. That's what we are doing here. Node to delete dot next equal to node to delete next to next. Simple, right?
Okay.
So here 3. Now you copied the value 3 from here to here, and you're changing the next node to the next node of 3. What is the next node of 3? 4. Now
Uh,
4 pointed to 5, 5 pointed to 6, 5, 6 pointed to 7. It's like, even if you have 1,000 nodes after this, we no need to worry, because all those already linked. 4 links to 5, 5 links to 6, 6 links to 7. It will go all the way to the 1,000.
okay, we are not shifting, just we are copying and removing the copied one, right?
Exactly. We are copying the data. We are copying the data from the next node here. We also copying the value. We are also copying the next value. What is the next value means wherever 3 pointed, we are simply putting here. It's a simple solution. You can say, you can in a realistic way, you are in a big line. Okay. You are in a, like five people are standing together, and they touched each, they linked with their hands. Okay. Now there is a big wall here. You don't know who is standing here. You don't know this guy name. You don't know, you cannot see his face, but you are standing here. You are asking, you are the commander. You're asking to delete this guy. Only thing you know is there is a hand here coming out. There is a hand. So simply what you are saying, okay, this guy, we are linking these two basically, and simply we are changing. Okay, move this guy to here. There is a place here, right? You cannot delete. There is a, this is a kind of in a ground, let's say. You simply say, okay, come here. This guy will come here, and this guy is already linking to the next guy. Simply we are changing. Okay, this is the place. You come here, and also the next two guy, you need to link next one here.
Yeah, got it.
Just like that, in a simple way. You don't need to move everybody, right? In a realistic way in the memory, right? So
Yes.
you simply saying what is the address of the next one. You are copying the value, and you also copying the address. And essentially at this point we need to delete the next node, right? Because it's a duplicate. 1 2 4 4 5. In case of 2, if you're deleting 2, it's like 1 3 3 4 5. So this node becomes like a duplicate node, right? So basically we are essentially deleting the next node, not the node which you are asking me to delete. Is it
But
clear?
main problem here is we generally need to pass the node, right?
We generally need to pass the node.
Sorry with my background noise. So the
Yeah.
thing is that generally when we are want to delete a node, we just give the number 3, which is an integer. But in this
Yeah.
format, we need to provide the node to delete.
Yeah, exactly. That's correct. That's correct. That's why if you look at the parameter, it's complete node.
Yeah.
Exactly. It's not the data. If I say delete 3, where is the 3? I don't know. You are not giving address to the head, and you're not giving the address to the node. How can delete 3? 3 could be anywhere in this 1,000 elements, right? That's exactly true. There's a difference here. If you compare the previous algorithm, here it says data. I know I can find 3. Let's say if there are 2 3s, I can delete the first 3, and I can keep the second 3. So data is fine if I have access to the head element, but if I don't know where to start, so I cannot even delete 3 if you give the data. That's why that's the difference here. Yeah, that's a good catch here. So this particular algorithm gives you the reference to the entire node. Yeah.
Thank you.
Cool. Yeah, essentially we are deleting the next node. This I can say here, like we are deleting the next node which has duplicate value. This is the deletion of the next node. Basically we are getting the address of the next node and giving it to the node to delete, that giving to the address of the node to delete. Cool. See that it's just like lines of 4 lines, and we discussed about 20 minutes, right? This is a really good algorithm. I would definitely ask an interview. Very simple. I can simply assess whether this guy prepared or not. That's only the main intention of this algorithms interviews are just to make sure whether you prepared or not. That's it. It does not tell you how much expertise you have in Java or Kotlin or what, or web development. Doesn't matter. It's only the main intention is whether you prepared to the interview or you just came to the interview just like that, right? So if you prepare like linked list, this is one of the things you can solve. Cool.
Yes.
Let's go to the next. Yeah. Next, go to the next one. So insert node at the correct position, right? So before going that, let me run this problem. If you want to see, So oh my god, show error. There's an error. Oh, here probably I forgot to put this one comment, I think. Come on. Okay. So here is the initial list: 1, 2, 3, 4, 5. List after deleting 3. 1, 2, 4, 5. Right? Try to delete 5. If you are trying to delete 5, you simply say this is last node. We need reference to the head node. So we cannot delete. Right? So
Yes.
here is the second, yeah, here is the second algorithm we are trying to do. Initial list is here 1, 3, 5, 6, 9. Okay, this is, if you look at here, this is ascending order, right? It's a kind of sorting order 1, 3, 5, 6, 9. Now list after insert 2. I want to insert 2. So it needs to figure out where exactly need to insert. So it has to insert after 1 and before 3. Right, that means basically 2 should be inserted, means it needs to update the address of the 1, right? The next address of the 1. That's what we need to figure out, right? List after inserting 4. If you want to insert 4, here is the thing: 1, 2, 3, 4. Right? So how to do that? Basically we need to update the node before that
Before
we
3.
want to insert. So yeah, so 3 next node, like we need to update, but we should not lost the rest of the elements. So 4 needs to join to the node 5, 6, 9, like that. Okay, so now if I say insert 7, it will be inserted here. If I say 10, it has to insert at the end, because 10 will go all the way to the end, right? Because that's a bigger number than any number in the current list here. So how to insert that? Now if I say insert 0, that should be the head, because 0 is a smaller number than any other number. So then it has to insert at the beginning, and in this situation you need to update the head pointer, otherwise you will lose 0, right? Until now head pointed to the 1 all the times, but as soon as you insert 0, you need to update the head to make sure 0 is the first element. How to do this? I think I already gave some hints here. So how can we do that?
So like first we have to find the position,
Mm-hmm.
and then when we find the position, and then suppose the position is p, so like we have to store the reference of p plus 1 somewhere, and then we have to like change reference in p minus 1, like we have to store p plus 1 reference in p minus 1.
Exactly,
uh,
exactly.
so
Yeah.
suppose the position is p.
Mm-hmm.
uh,
Yeah. Basically, you need to, what you're saying is we need to find the exact position, and by the time you find the position, you need to have access to the previous node. Position minus 1 means, like you are saying, previous node, access to the previous node. That way you
yeah
have full handle of this node, right? So if you want to insert 3 here or 2 here, you need to have access to 1, and you know that it should replace, or it should take the place of 3. That means it should be the second element. That's the position. Yeah, that's exactly right. So here is the algorithm. I will show the algorithm directly. Here is the head pointer. As I said, this is straightforward. It's not like the previous question is like there is a head always be there, and here is a new node you want to insert, and here is the algorithm. Okay, if head equal to null, okay, this is a base condition. That means we don't have any element. What happens? The new node is the new head, right? So basically this particular algorithm returns the updated head, whatever the new head after the inserting, right? So if the given list is empty, return new node, it will be the head simply. This is the base condition. And if say this is the second condition, let's say inserting 0, let's say the head dot data is greater than the new node dot data. That means whatever the node you are adding, the data is smaller than the head node. That means the first node itself has a larger value than the value of the new node. So insert the node at the front of the list. You no need to navigate anything. You know that, right? 0. So if 1 is greater than 0, right, then you no need to worry about rest of the nodes. You definitely, they already said it's ascending order. The rest of the nodes already greater than 1. You no need to navigate anything, because first node itself has a big value. Head has a big value than the value you are trying to insert. Simply what you need to do, new node dot next equal to head, and return new node, that will be the head. New node will be the new head of the list. Simple, just very simple. So we are changing the next pointer to the head of the node, head of the list. Is it clear, or do you want me to draw and explain? One, two, let's say 1, 2, 1, 3, 5, 4. Sorry, 1, 3, 5, 6, 9. Right. So we want to insert with value 0. Let's say that's the condition we are checking. This is the last condition, right? So 0 is like 1 is greater than 0. That's the condition we are checking at the line number 139. Correct? So since that is the case, what we need to do is we simply change new node dot next equal to head. This is head pointed to 1, right?
Yes.
Is it clear? Yeah. So Modit and Soumya, you guys, are you clear on these two lines?
Yeah, Suresh.
Yeah.
Cool. Yeah. So once we have those two, we can go to the next section where we want to delete something in the middle. Like, not delete, we want to insert somewhere in the middle. So simply, as Modit said, we need to take the current pointer equal to head, and we need to do a loop. This is the main important condition of this one. So we need to see whether the next element is not equal to null, and the next dot data, if the next dot data is less than this data what you are inserting, right,
Okay.
then you simply go ahead. So now let's say you want to insert 2, right? Let's iterate that. So new node equal to true and current equal to 1, right? So current we initialized with head, so current equal to 1. So now what are we doing? Current dot next not equal to null, current dot next not equal to null, and current dot data is less than new node dot data. That means 3 less than 2. Is it right?
Yeah.
Are you guys following? Is it right or wrong?
Yes, it's clear.
No, I'm asking, is it right or wrong? This is false,
Okay, so
right?
this false.
This
This condition is false.
false.
So immediately it will come here. So now we either found the correct place of the node, which is after the current node, or if the current node dot next becomes null, that means all the nodes of the list have lesser value, not SSER, lesser value. So I will come to that point later. So now new node dot next equal to current dot next, because the current dot next, which is the value, is greater than the value of the new node. Simply we are saying new node dot next equal to current dot next. Current is 1, right? Current pointed to here and new pointed here. So whatever the next value, new node dot next pointed to the current next, and current dot next pointed to the new node. So simply 1, 2, 3, 5, 6, 9.
9.
This is main two. These two lines are really important here to understand. So in this situation, head did not modify, right? Head is still pointed to 1. That's why I'm returning head here. no changes to the head. But here you changed the head. You added new node as a head. That's why we are sending new node as a head to this algorithm, to this method. But in this case, you did not modify head. Head is still pointed to 1. So you simply inserted 2 in the middle. So you are returning head here. I hope it is clear. So let's say 7. If you want to insert 7, so what happens is current will go to 1, 2, 3, 1, 2, 5, and then we will see, and 6 as well. And now current dot next value is 9. So that's where it come here. So by the time the loop exit, the current pointed to the previous one, basically the previous node, 6. That's where we see like next node dot next equal to next. So if the new node is 7, so 7 dot next will point to the 9 and 6 point to 7.
Yes.
That's the thing. Current dot next. These are all things like you need to be very careful while changing the pointers. Very careful. Otherwise, it will screw up the entire algorithm. Right?
Yep.
Yeah.
Yes.
Now the next condition, the last final condition is, let's say you want to insert 10. So current will go from 1, 3, 5, 6, 9, and 9 dot next equal to null, right? That's the condition it will fail, because none of the, every time the value is greater. 10 is like current dot next is less than new node dot data. Yes, 10 is greater than, or you can say it different way. 1 is greater than 10. 2 is greater than 2 is, sorry, 1 is less than 10, 2 is less than 10, 5 is less than 10, 6, 9 also less than 10. But by the time 9, right, 9 dot next, current is 9, 9 dot next is null. So this is 9, since 9 is the last element, right? At that situation, we are simply saying node dot next equal to current dot next. It simply still works the same way. Current dot next is null. That means new node dot next equal to null, and current dot next equal to new node. Current pointed to null. So 9 pointed to 10. So we
Yes.
no need to write any special logic for last element, because by the time you complete the loop, there are two cases can be possible. We either found the correct place of the new node, which is after the current node, if the current data is greater than new node. If the current dot next becomes null, it means all the nodes of the list have lesser value than the value of the new node. So add the node at the end, which is after the current node, because current node pointed to the last node now. I hope it is clear, right? If the
Yes.
current pointed to the last node, again last node dot next always null. So that's what we are putting here. Modit, is it clear?
Yeah. Yes, Suresh.
Yeah, it requires practice. Always, like even though lines are just 4 5 lines, these conditions and these kind of changing the pointers always requires practice. Yeah. So this is how to insert a node, this particular ascending order. Okay. So that's about the insertion sort, because you can do it sorting algorithm. Actually, there is a, I can also explain that. Basically, in this algorithm, I already set the list already in a sorting order, right, ascending order. But if I gave you the list which is not in a sorting order, you can use this algorithm which I just discussed. This is called insertion algorithm. You are inserting a node, right? You are finding the correct position, and you are inserting a particular new node into that list. So we can use exact same logic to write the sorting algorithm in linked list. So I will give you a list which is not sorted, but you can make it sorted. Yeah, we can cover in the next week if possible. Cool. These questions we can cover next week. This is the whole thing. And complexity is all order of n always, because we are at the worst case we will navigate all the nodes of the node. That's the worst case, and that's the complexity.
Yep.
Cool.
Yes.
Okay, I think I went over a lot today. I think let me know if any other questions. Otherwise, we can wind off. It's already late for you guys, right? Any
Me,
questions?
fine.
It's evening for you, I think.
Yeah, yeah.
Well, is it good, Modit or Soumya? Any questions so far? I will send the other them.
No, mother. Sorry. No, sorry. I don't have any questions.
Cool, great.
Like,
Okay,
like
I will send the algorithm to this. Yeah.
Yeah.
yeah, I was saying like
Okay.
it's fun to discuss, like have this discussions and solving questions.
Exactly. Definitely helpful. Yeah. Yeah. I'm going to stop recording now.